Wow, thanks for showing up here. I'd like to present to you a project. It came out after doing many one-off projects. So in a way, it's like an attempt to make the ultimate framework. But first, let's have a look what people in DIY audio are doing. When you look around here, and people do audio, they make analog circuits, or they modify existing circuits called circuit bending. Like you have the speak and spell, they modify it and do different things. Or they make MIDI controllers as an extension of their laptop to have a new way to control it. I saw a really nice one, a wooden MIDI controller yesterday around here. And then there is people doing sound with 8-bit microcontrollers. I mean, like going like sort of hybrid topology, making like digital pulses from software and using the pulses as sound. And then there is real embedded digital signal processing. That means you're not dealing with just pulses, but accurate measurements and time domain processing in a digital world that could create just any waveform, not limited to square waves or chip tunes. There's very few digital signal processing DIY happening because it needs quite a setup. This is what digital signal processing is about. So you have sound input, you convert it from analog, from a continuous waveform to digital numbers at regular time intervals, and then you have a processor which runs some sort of software. Can be controlled from MIDI or from a front panel with knobs and dials. And at some point it can go back to analog sound. A computer can do this actually very well. There's lots of software around, open source, closed source, for every taste. It's sort of crowded in this field. So there's software synthesizers that emulate old analog machines or new things that were impossible to create with analog machines. It's very crowded. Apparently, if you go to a music instrument store, there's still a lot of dedicated hardware. People like to play a dedicated instrument because it's plug and play. You just turn it on, and it always works. It's not designed for office work, and it will not show you email notifications. It's really quite distracting if you do a jam session with friends and you work with a laptop. There's often something that sort of pop-ups, or you updated something, you start like testing things rather than playing. So I designed some hardware that is exactly this, like analog to digital converter, digital to analog, and a processor. So you see like stereo input, stereo output, a headphone jack, a USB port for computer connection, a slot for an SD card, and MIDI input, MIDI output. It's very similar as what is inside the things you can buy in a music instrument store. Because if you would take these things apart, you would see that the inside is sort of similar. It's just they make a lot of products differentiated by the shape, the number of knobs, and the color of the plastic. And the firmware running on it. I didn't do the knobs and the plastic. So there's front-side connectors, and then on the back end there is like general-purpose inputs and outputs that allow you to connect almost anything. A bit similar like Arduino. It's really not limited to knobs and dials. You can also do servo motors or accelerometers or light sensors, whatever you can think of. It's more like circuit bending as a goal than as an afterthought or as a mod. So to get this thing talking, we need to develop some digital signal processing firmware that breaks apart sort of in a audio input-output driver, a media input-output driver, other input-outputs for front panel knobs and dials, and then you make any combination of digital signal processing algorithms like oscillators, filters, envelopes, and then you have to map the parameters to control it somehow, and some bookkeeping to load new presets or things. It's not the first time that open source embedded DSP solutions have been developed. But they didn't really reach critical mass. I think programming DSP can be sort of complex. There is mathematics involved. For example, you have to make trade-offs between execution speed and quality. For instance, the standard CMAT library is of sort of limited use. It's made for mathematical precision, and sometimes you really want to go much faster than that. It's not because you could edit or add DSP algorithms to firmware that someone will do so. Now I'm going to make a little switch to what's out there in software, in pure software without going to hardware. There is several data flow-oriented programming languages. The main open source one is Pure Data. So there's a program where you select objects, you put them on the screen, you configure them, and you put wires between inputs and outputs, and this turns into a program. And your document is a program, so it's a sort of programming language. There's a commercial variant called Max, and they have a similar syntax and grammar. The nice thing about graphical programming is that you can't make errors against syntax or grammar because you choose your objects. You don't have to really type code. So it's you can only make errors against the logic. So the punishment of making an error is much smaller. You don't get a compiler saying like, I don't understand it. It will just do something, and it's up to you to make it do the right thing. So with this low punishment of experiments, it's very accessible to artists and musicians, and so around both languages there is quite a community of artists developing all sort of things. It's a graphical programming language. It's not. I wouldn't say it's a complete It's not a complete programming language. I wouldn't implement a quicksort in any of these by patching things around. That really gets awkward. But signal processing is really about regular data at regular intervals, and the execution part of the code is really boring. It's really linear. both environments depend on objects are loaded as dynamic loaded libraries. So at runtime, it needs to dispatch function calls from two DLLs, which implies a huge overhead if an object just needs to add two inputs together. So the processor needs to make an indirect jump, save the context, add, and then restore the context. While this probably could have been one instruction in optimal code. So let's try to make editing firmware similarly as easy as possible. So I wanted to make a graphical data flow programming environment for firmware that does not expose command line tools, does not expose C++ code, unless you would want to, and easen the compile, upload, and run cycle. So that was the first version of the architecture. So on your computer, you would run a program, the Axoloti patcher. This one has like a library of objects you could put on the screen, wire them up, and that software would generate code, compile it, and upload it. And then this is the Axoloti core. That's the board. Yeah, we have the camera at the wrong place. Could someone put the camera over here? So after uploading, you have the Axoloti core programmed with the right firmware. You can do sound I/O, MIDI I/O, and general purpose I/O. And after flashing, you just turn it on, and you can play. I'll give a little demo of that. So this is the patcher environment. So this empty document, and with a double click, I get the object library. I have like a linear catalog, an alphabetic catalog of objects. We also have like a hierarchy of categories, which makes it easier to search. You can also start typing a name and it will like find the best match. So I start with, as an example, with the sawtooth wave. So this selects a sawtooth wave oscillator. Sawtooth wave is like a linear ramp, periodically repeated. So let's have a look at the anatomy of this object. It has like an input on the left. The blue color is a data type. This means it's for modulation, control voltage. Like it's for slow changes, not suitable for audio quality, but good enough for changes over time. And then there is a red data type, an output on the right. Both have indication. Plus minus means that they're like bipolar. And then there's a dial where you can adjust the frequency. I tried to make it as user-friendly as possible. So at the 0 position, it would give a certain value in hertz. If musicians want to read the note, the name of the note, that's one click away. And you also get the factor compared to the middle value. So if I would put the dial on at 12, I can just type 12. You see that the ratio is ×2, so 12 semitones in music corresponds with a double frequency. And at the same time, you can also wonder if with that 7 semitones corresponds with almost 1.5, which almost directly shows how harmony works in music. So to listen to the oscillator, I have to add I take a volume control just to be safe with the sound system. Oh, I have a multiply object here, multiply with a constant. So there's a dial to adjust the constant. But I created a blue object. I mean, blue input, blue output. But similar like you have like function overloading in C++, this object will upgrade to a red one. Because it sees, oh, you give me a red input, and there is a red implementation of this object as well. And then I can wire that to the output audio out stereo. Dial it up. So the first version was this: you press a button and it will generate C++ code, and it would be uploaded to the target. And if everything works, can you turn the volume up a bit? Are you, oh, I unplugged something. Turn it down first, please, the external input. Okay, so here you see that you already get a working system. I'm actually jumping in my presentation because version 1 was just you make a chart with your program and it would run that. Version 2 was about making the changes interactive. So after generating C++ code, compiling it, doing the upload, make it also instrumented, that you can change parameters on the fly. So that you don't need to go to a recompile and re-upload cycle for just adjusting a number. And it also goes the other way around. So you see 2 level meters here that will also read back from the code and show you the actual volume level. So no computation, no critical audio computation is going on my laptop. It's the firmware that is compiled and uploaded that is talking with the user interface after it's running. So, okay, we have a little oscillator, and if I can turn this very easily into a music keyboard. If I take a keyboard object, and the keyboard object has an output for the note that's being played, and there's a gate output that will indicate when a key is pressed or not. It's very similar in reasoning as old, well, they still made analog synthesizers, analog modular synthesizers. You have like machines where you have like it's a bit similar to this, but every object is like a circuit, and you interconnect them with patch cables. To grow up to a playable thing, I have to modify the volume depending on the gate. The yellow cable type is a Boolean, on or off, but that also can convert into a blue one. There doesn't need to be a substitution object that has a yellow input, because there's a conversion rule from yellow to blue. So I turn that on, and I take a virtual keyboard. Oh, volume is still at 0. Voila. So we have a playable system. I thought 5 objects would be a bare minimum to get a playable system, but it can grow quite a bit. Let's go into, I'll take a little organ patch. Organ. Okay, so there's like a sort of a so one of the problems if you want to play music, you don't want to be limited to one key, because well, some instruments do. For some instruments, that's reasonable, but for an organ, it's not reasonable. But if you want to express that in a patch, it's sort of awkward. If you would have to wire up 12 or 16 different oscillators and pots for if you want to play different keys. So I made a way to use one document as an object into another one. So actually this object comes from this patch. This document has like magic objects. It's called an outlet object that represents an output on the generated object that corresponds with it. Also here there's a little the red output, and inside it just uses a keyboard object like I showed in the beginning. So that's the child patch, and then on top I asked, give me 12 voices of that, and just arrange it. But I also wanted to show that inside this object, some parameters have like an attribute. It's called parameter on parent. So the parameters with this flag set, they are promoted to the object corresponding with the inside object. So that's 12 voices of a certain architecture to play one organ pipe or something. So and then I can change the inside parameters. So the rest is just a matter of combining elements and adding objects to the library, up to currently I think there's over 400 objects serving different purposes, and it seems to be that's like the critical minimum. Critical minimum has sort of been reached, that you can start doing stuff without having to write another object for a certain purpose. Let me show you something that, if you're used to Arduino or things, that might give it a different look. What I did on this setup is wire a potentiometer to analog input, so it's just a regular voltage divider. Like this. So it takes power supply, ground, and feeds that into the potentiometer and gets back the analog input. So instead of in Arduino, people learn to write like a function call called analog read. In my environment, it's called GPIO in/analog, and I select the channel where it is connected to. And in Arduino, people learn how to print numbers to a console and read the numbers that fly over there. Here I can have a little chart plotter or a dial, or or a numerical readout. No, it's already in the dial. Don't need that. So if I turn the knob, you see it's instrument. You don't have to watch the flying numbers. You have like the oscilloscope on screen. So I think that's quite a bit more learnable than writing the same thing in C and then getting a terminal with numbers flying by. In the same world, you can also do PWM to drive a stepper motor, or dim LEDs, or do SPI or I2C. As a final demo, I take a bit of. Well, I'm not really a musician, although I sometimes enjoy playing something. So on top there's like a little. This is a metronome, a square wave generated at 5 hertz. That means 340 BPM, but it's divided in steps, so it's not really 240 BPM. And then like a counter that counts to 16. If the counter does a carry, there's another counter that will count to 4. When that does a carry, also something else will happen. And then there are steps and patterns, and oscillators and generators and stuff. So, but I thought I would like make a modification to this document. Otherwise, it's so boring. I take this GPIO in analog object, and I have like this little 2-channel mixer to recombine influences. Okay, quickly. No, I just skip the analog input just for the time, and I press live. So there's like a drum machine and a hi-hat and a bass line. These are no samples involved, it's just all algorithms. That means you have a lot of flexibility.
So that's a very nice demo. Yeah. So, thank you very much. I'm afraid we don't have time for questions and answers right now, but if you're interested in Johannes' work, then just come up to him right after the talk and maybe find a place to meet somewhere. So please give him an applause.